Hello everybody. What I'd like to do in today's pre-lecture is go through a couple of different concepts. The first is recognizing the difference between ionic and covalent bonding, so that's the first thing. And then I'd like to talk about empirical and molecular formulas, and if we have time, how we actually calculate an empirical formula. Okay? So we're actually moving outside of atoms and elements, and even we did talk about compounds, but now we're actually going to look at, well, how do we form these compounds? What is this thing called bonding that's going on? And then we're going to look at how we represent formulas as well. So let's get to it. And so this is a figure that shows how an ionic compound forms. We also call ionic compounds salts. And this is a salt you're very familiar with, right? This is table salt, sodium chloride. Right? So we know that salts typically are crystalline, so look down here at the bottom, crystalline solids. Okay? We'll talk a little bit about the difference in properties between ionic and covalent. We'll do more of that in class as well. So what we have is, and we're not quite there yet, but what we have is a sodium atom that has one valence electron, one outermost electron. And we're going to start looking later in this course about what electron configurations and where the electrons are. But just take that for now, and you might remember this from a high school course, but sodium has one valence electron. Chlorine, on the other hand, choose a different color here, has 7 valence electrons. We're going to draw the electrons as dots. All right? And what we're going to find as we go on in this course is atoms will tend to gain, lose, or share electrons to achieve an octet of electrons, 8 electrons. So we will have, atoms will gain, lose, or share electrons. Sorry about that. All right, and that's how we're going to go, approach bonding, is that something might lose something, an atom might lose an electron, another atom might gain an electron, but they're both, in a sense, trying to achieve the same thing, an octet of electrons around that atom. Sometimes electrons might be shared, and we're going to get to that as well. So you can envision what happens here if sodium transfers that one electron to chlorine. Chlorine will certainly now have 8 electrons, an octet. Right? And it's also then, once chlorine gains that electron, I didn't leave myself enough room here, so I'm going to go down to the bottom. So now if we draw chlorine with an extra electron, it gained a negative electron, so it's going to have a -1 charge. Sodium has now lost an electron, so it now has a positive charge. So we've talked about cations and anions. It's always a change in the number of electrons. Right? To form a cation, we lose electrons. To form an anion, we gain electrons. So now we have these two ions, and they are going to be held together by what we call an electrostatic attraction. Okay. More simply, attraction between oppositely charged ions. Okay, so oppositely charged ions are going to attract each other. If they have the same charge, they're going to repel each other. But these are oppositely charged. They're going to attract each other, and that is what we call an ionic bond, or what we call ionic bonding. Okay, this attraction between oppositely charged ions. One species, typically the metal, has lost an electron or electrons. Depends on what type of metal it is. The other species, quite often a non-metal, has gained an electron or electrons. In this case, loss of 1 electron by sodium, gain of 1 electron by chlorine to form chloride. All right, and that's what we call ionic bonding, this attraction then between these oppositely charged ions. Now you will notice, as we show here in the middle, that salts or ionic compounds exist as a large collection, a 3-dimensional lattice of these ions. Okay, so it's not just one sodium with one chloride. It's a whole extended 3-dimensional structure. Okay, And that's why we see these crystalline aspects of salts, because it's this extended ordered structure. Okay? Extended 3D, three-dimensional lattice that has a high degree of order. All right, and that's why we see this crystalline nature, very ordered, repeating structure of sodium ions and chloride ions. Okay, lots of stuff in that one slide there, but what I want you to really focus on is when we form an ionic compound, one species is going to lose electrons, that's typically a metal. Another species is going to gain electrons, that's typically a nonmetal. I'm going to show you other types of things we're going to focus on as we go on in this course as well. Then we have a cation and an anion that are held together in an extended structure, electrostatic attraction of positive and negative ions. That's what we call ionic bonding. Okay. Now I said it's quite often a nonmetal that gains the electrons. It could be something, and I apologize, I should have left myself a little bit more room, but I have more notes below. Let me just try to put it here. Let me go to a different color so it stands out a little bit more. There are things that are called polyatomic anions that are formed. And you're probably somewhat familiar with some of these. I'll just put a couple. So something else that could gain electrons is this thing that's NO3 as a unit, and that would gain one electron and form a negative one ion. That is called nitrate, and you've probably heard that term before. Another one that can gain two electrons from, say, from a metal is carbonate. Okay, and let's just do one more. One grouping of atoms, and again, this one, P with 4 oxygens, as a unit can gain 3 electrons and have a negative 3 charge. This is called phosphate. And I'm sure you've heard these terms before. These are very common polyatomic anions that in nature would be combined with metal cations. Nitrate, carbonate, phosphate could be combined with sodium ions or magnesium ions or calcium ions or something like that. Okay, so that's kind of the other thing that could make up an ionic compound. Nonmetal anions or polyatomic anions combined with a metal cation. Okay? All right, well, let's scroll down a little bit and look at something that's a little bit different. Now, this reaction up here is between, one thing I want to point out about this reaction just from an interesting standpoint, I always kind of crack up when we do chemical reactions, and I crack up easily, as you know. But sodium is a highly reactive metal. You throw a chunk of sodium into water, and it's a pretty violent reaction. Hydrogen gas is produced. That hydrogen gas can ignite. You may have seen the reaction of sodium and water. If you haven't, just go to YouTube and Google sodium and water, and you might find some pretty funny things out there. But if you ever mess with sodium, be careful. It can be quite dangerous. So here's this highly reactive metal that you certainly wouldn't want to eat because it would react in your mouth, produce hydrogen gas. The hydrogen gas would ignite. Not a good thing. Chlorine gas is a toxic gas. Okay, nasty stuff. So we have both reactants in this case, sodium and chlorine, that, boy, you wouldn't want to mess with. And yet when they combine to form a new compound, okay, a chemical reaction, we're making and breaking bonds. We're breaking bonds in sodium, we're breaking bonds in chlorine to form these new sodium chloride ionic bonds. What do we do with that stuff? We eat it. It always just kind of boggles my mind that we take these two nasty substances that we wouldn't want to put in our mouths, obviously, but then the compound that's formed from those is something that we actually eat. All right, so let's look at chlorine and see how that's different from sodium chloride. First of all, it's composed of nonmetals. Okay, it's only one nonmetal, chlorine. Okay, nonmetals, when they combine, are going to form a different type of compound, a different type of bond. So let's kind of look at what's happening here. Let me scroll down so I can get a little bit more room. So again, let's go back to chlorine. And if you don't understand why chlorine has 7 valence electrons yet, that's okay. We will do that later in this course, but I want to give you an idea about what's going on. I should have drawn the electrons in the other chlorine a different color. In particular, let's draw that one a different color. Okay. Now, each chlorine has 7 valence electrons. Each one wants 8. If I were to transfer one, okay, well, then one chlorine gets 8, the other one only has 6. That's not good. So what happens in this case is the chlorine atoms are going to share electrons. And we're going to end up with something like, let me go back to green since I was dealing in green. Okay, we're going to have one electron from one of the chlorine atoms, one from the other one shared between the two, and then all the other electrons will remain on each chlorine. Okay, so they're just sharing 2 electrons. One from one chlorine and share with one from the other, and we count those shared electrons for each atom. So we're going to count those 2 electrons with that chlorine, but then we're going to kind of overlap it and count those with the other. So we're going to count 8 electrons for each chlorine atom in that chlorine molecule. So this is a diatomic molecule, 2 chlorine atoms to form a chlorine molecule, and we would then look at that bonding. We've reached the octet. We'll do more with that as we go on and learn more about where electrons are, and we'll do more with bonding later in the course, but I wanted to introduce it here. This type of bond is clearly different than an ionic bond, right? Clearly different. An ionic bond, one thing gave an electron to something else. Here, they're sharing them. Okay, nobody wanted to give up an electron. I'm keeping my electron, you keep yours, but hey, we'll get along, we'll share. All right? Nice chlorine atoms, okay? So there's our chlorine molecule. This is a different type of bond that we call a covalent. Oops, I spelled it wrong. I got ahead of myself. C-O-V-A-L-E-N-T, covalent bond. In a covalent bond, electrons are shared. And this is typically the type of bond you see between nonmetals. Okay? So remember, ionic quite often is a metal with a nonmetal. Covalent compounds are typically compounds of nonmetals going to share electrons. All right? Try to think if there's anything else I wanted to say about these. Oh, these are different. These, as you can see up here, these do exist as individual molecules. As opposed to ionic, which does not. All right? So the ionic, there's not an individual NaCl molecule in here. Okay, there's lots of sodium ions, there's lots of chloride ions. All three-dimensional structure, right? So why do we write the formula of sodium chloride NaCl? Because it doesn't exist as one Na with one Cl. It doesn't exist that way. But why do we write it that way? It's because that's the ratio at which they combine. It's one sodium combined with every one chloride, even though there's many sodium ions and many chloride ions alternating throughout that structure, their ratio is 1 to 1. All right? Now, technically, just to point something out, it's not actually correct to say a sodium chloride molecule because it doesn't exist as a molecule. But you will hear me say it, and I won't blame you for saying it either, because technically what we're supposed to call that sodium chloride unit is a formula unit. And I just don't like formula unit. It just sounds kind of, I don't know. So I will refer to sodium chloride as a molecule, but make sure you realize if I'm talking ionic, and if you're talking ionic, when we say a molecule of an ionic compound, we know that really doesn't exist. It's really this extended three-dimensional lattice. Whereas in a covalently bonded compound, we in fact call these molecular compounds because they do indeed exist as individual separate molecules of that substance. Make sure you note the difference there. Okay, I think I'm about halfway through here. So ionic and covalent bonding, have a feel for the difference. Transfer, you have electron. One substance loses electrons, one substance gains. Electrostatic attraction, that's ionic bonding. Sharing of electrons between nonmetals, covalent bonding. All right. One thing before we get to empirical and molecular formulas I wanted to show you, as we start looking at formulas, there's a lot of different ways that we can write them. And this is a compound called methane, which you've probably heard of. It is natural gas. There's some other things in natural gas, some things that we actually add so we can actually smell it to make it safer. But natural gas is methane. and it has the formula CH4. It's composed of nonmetals, carbon and hydrogen, and so this is a molecular compound with covalent bonding. All right? So this does exist as individual molecules. So the simplest way we can write it is, for every one carbon there are 4 hydrogens. We write this molecular formula, the formula of that molecule. Now, we can do a little bit more detail by putting some bonds in, and these are what we call single bonds. And I didn't show this with chlorine above, but I will talk about it here. A single bond is a 2-electron bond. So that bond between the 2 chlorines, where the 2 electrons were shared, we could actually draw a line between those 2 chlorines and to represent a single bond between those 2 chlorine atoms. Okay, same thing here. We're showing a single bond between carbon and each of those hydrogen atoms, 2-electron bond. As we go on in this course, we'll find we can have double bonds and triple bonds as well. We can show a little bit more detail by going to a model, and we will actually build models later in this course where we show the carbon in black and we show the hydrogen in gray. And there are typical colors that are used for atoms. Carbon is typically black, hydrogen gray, oxygen red, nitrogen blue, and so on. I'll show you that in class. Now, I'm not a big fan of ball and stick models. It's when we build a model, that's what we build, just because our model kits are kind of like that. But it gives you a false sense of that electrons are localized. They're very fixed in a small region of space between those 2 atoms. In fact, electrons are in constant motion, and they're more spread out in that region between the atoms. And so a space filling model is a more accurate representation of the electron density in that molecule. Okay. Now, these we don't build models for these, but you'll see these in the textbook a lot, where this gives a better representation of how the electrons are spread out. It's just not a stick of electrons between the atoms in the molecule. Okay, so that's how we represent molecules. Let's talk a little bit more about different types of formulas. And if we have time, I think I'm it's at 16 minutes. I'm going to try to keep this to 25. We might actually calculate a formula. So the molecular formula is the true formula of the compound. So for methane, this is its molecular formula. That's how it exists. That molecule has 1 carbon and 4 hydrogen atoms that make up that molecule. Okay? It is the true formula of the substance. Okay? We're going to deal with empirical formulas as well. They are the simplest whole number ratio of how the atoms combine. The simplest whole number ratio of how they combine. So probably the best way to illustrate this is with an example, and that is I have benzene here. This is the actual formula of a benzene molecule. Okay, so this is the molecular formula. You probably don't know that. It's a pretty common organic solvent. So particularly if you go on to organic chemistry, you will hear a lot about benzene. But that is the true formula of benzene. There are 6 carbon atoms in a ring, and to each carbon atom there is 1 hydrogen atom bonded to it. But that is how it actually exists as a molecule. But could we write a simpler formula than that? A simpler whole number formula? And sure we can in this case. We could divide each of these subscripts by 6, and we could have a simpler formula where it's essentially showing us 1 carbon combines with every 1 hydrogen, that ratio of 1 to 1. This is the simplest whole number ratio. We would call that an empirical formula. All right? That's all there is to it. Now, let's go back up to methane, since I have it written up there. That is the molecular formula. Can we simplify that into a simpler whole number formula? In this case, no. The subscript of carbon is already 1. That's the smallest whole number, positive whole number. I guess whole numbers are greater than 1, so that is I guess 0 is a whole number as well. But in terms of, you get the idea. We can't go below 1. So that is the simplest. So this is also an empirical formula. I didn't say that very well, but I hope you get the idea. Its true formula is CH4. We can't simplify it any further. It happens to also be its empirical formula. So you might find that to be the case sometimes. Okay. Couple more things before we actually maybe get a quick calculation in. We've kind of talked about what these subscripts mean. I think that you are aware of this first way to read subscripts, and that's how we kind of just read it with methane. One carbon atom with every 4 hydrogen atoms in one molecule. Well, same thing here. In one molecule, this is actually called carbon tetrachloride. There is one carbon atom, okay, subscript of 1 is understood, for every 4 chlorine atoms to make up that one molecule. But, and we're going to do this quite often, we can actually read it as a mole ratio as well. If we had a mole of carbon tetrachloride, so we've just scaled up, we've gone to 6 times 10 to the 23rd molecules. Okay, so now we have a huge number of molecules, which we simplify and just call it a mole. Okay, if one molecule has 1 atom, 1 mole of molecules is going to have 1 mole of atoms. So we can read these subscripts as a mole ratio. There's 1 mole of carbon for every 4 moles of chlorine. Okay, so in 1 mole of that compound, there's 1 mole of carbon, 4 moles of chlorine. That might seem a little odd, but it's just scaling up from 1 molecule to 6 times 10 to the 23rd molecules. The ratio of 1 to 4 is going to stay the same, whether we're talking 1 atom of carbon, 4 atoms of hydrogen, going all the way up to a mole of carbon to 4 moles of hydrogen. Okay, try to see that. It's very important that you do, because that will help us determine our empirical formula. So let's just jump to this practice problem. And this is what's really important to solving for an empirical formula. I think I have about 4 minutes left, so let's at least get started. We'll practice more of these in class. So if I know that the subscripts can mean a mole ratio, I should be thinking, boy, if I can get the moles of substance, each thing that makes up that compound, I should be able to figure out the formula. And so what we're going to deal with is what's called mass percent data. Okay? And so you could look at a compound, and this is actually a very common experimental technique. You send a molecule you make off to a lab, they'll run an elemental analysis on it and tell you the percent by mass makeup of the molecule that you made. Okay? So this compound is 74.875% carbon, the remainder is hydrogen. So the first thing we need to do is get the percent hydrogen by difference. So subtract that from 100. So our percent hydrogen is 20. Oh, I think I did this number wrong. Hold on. No, I think that's right. 25.125% hydrogen. Okay. So those are mass percents. Okay. So how are we going to do this calculation? Well, one thing we're going to do to help our calculation is assume we have 100 grams of substance. Now, why the heck would we want to do that? To make our lives easier. Isn't that our whole goal in life, to make our lives easier? Because these percentages, since they are a mass percent, if you take 74.875% of 100, guess what you're going to get? 74.875 grams of carbon. Okay, we just want to make our lives easier in our calculation here. If you want to make your life harder, you can assume a different amount of substance, but let's assume 100 grams. We're going to do the same thing. Since we assumed 100 grams, we'll have 25.125 grams of hydrogen. Now, here's the calculation, and you know how to do this calculation already. We want to get to moles. Why do we want to get to moles? Because we can read those subscripts in a chemical formula as a mole ratio, just what we talked about. Do we know how to get to moles? I hope so. 1 mole of carbon, 12.01 grams of carbon. Where do we get that? Periodic table. That's the molar mass. Hydrogen. 1 mole of hydrogen, 1.008 grams of hydrogen, directly from the periodic table. And we do our calculations here, which you know how to do already. So really nothing new here. 6.234 moles of carbon. And 24.926. I think I carried an extra sig fig there, but that's okay. We're going to get to whole numbers anyway, hopefully. And there is our mole ratio. Okay, for every 6.234 moles of carbon, we have 24.926 moles of hydrogen. So we could actually write that as a formula. This is going to look pretty, oops, sorry, what happened here? Going to look pretty funky, but it still is a formula. That's the correct ratio of carbon to hydrogen. But is that how we write formulas? No, we typically write them with whole numbers. So how do we get to whole numbers? Well, you know, some of you might be thinking, well, why don't we just round that 6.234 to 6 and round 24.9 to 25 and call it a day? No, that's not what you should do, because you really only want to round if you're really, really close to a whole number. This is not close enough. But what we're going to do is we're going to divide by the smallest number. Now, why would we want to divide by the smallest number? Because we're guaranteed to get at least one whole number, right? So when we divide 6.234 by 6.234, we're going to get a whole number, and that whole number is going to be 1. So we're going to get 1 for carbon. What do we get for hydrogen? So we get hydrogen 3.998. All right, well, what do you think about that? Do you think 3.998 is okay to round to 4? Yes. That would be okay in this case. Remember, you know, if you actually send off to a laboratory, this is experimental data. You don't expect it to be exact. All right? So our empirical formula in this case would actually be CH4. Kind of got back to methane, didn't we? Well, that may or may not be methane. That could, you know, the molecular formula might be some multiple of that. And we will talk about how you go from an empirical formula to a molecular formula in class. Okay? So, lots of stuff. I think I went a little over 25 minutes. Sorry about that. I'm always shooting for 25 minutes. Not guaranteed. But, again, just to sum up this problem, that'll be it for the pre-lecture. We can read the subscripts in a formula as in 1 mole of that compound, how many moles of each component do we have? A mole ratio of how, in this case, carbon and hydrogen combine in this example. So make sure you know that. We'll have mass percent data. So a good assumption to start with is 100 grams, because then those percentages convert directly to mass in grams. We know we need to get the moles because we can read those subscripts as a mole ratio. Once you get the moles, divide by the smallest number, so you at least get one whole number. In this case, both of our both of our things came out to moles. I have no idea why that happens to do that. I did not touch anything on my computer at that point. Both of them came out to whole numbers. Now, sometimes you might not get whole numbers at this point, but you'll be a lot closer, and we'll talk about what you do. But in this case, we got to whole numbers, and there is our empirical formula for this compound. May or may not be a molecular formula. We need one more piece of information to figure out if that is a molecular formula or not, and we will do that in class. Okay, sorry for running over a little bit. See you soon.